All right, in this video we're going to talk about electrolytes versus non-electrolytes. We'll talk about ion concentrations, and we might get into molarity. We'll see how much time we have. So, to talk about electrolytes versus non-electrolytes. So, certain characteristics. Electrolytes, in order to have an electrolyte, you need to have ions in solution. Okay, so that means ionic compounds, acids, no, not AIDS, acids, got the C there, bases, right? Things that make ions in solution. Okay, and the defining characteristic of an electrolyte is that it will conduct electricity. Okay, electrolyte solutions conduct electricity. And before I get into that, so non-electrolyte solutions are in this sort of general category of covalent solutions. Okay, things that don't have ions in solution. Right, and as you might expect, they don't conduct electricity. Okay, now, contrary to popular belief, H2O by itself lives in the non-electrolyte category, okay, because pure H2O has no ions. Now, tap water, seawater, rainwater, all of those things have plenty of ions in them, okay, because it's not pure H2O. So that's why it's dangerous to be standing in a puddle in a lightning storm, that sort of thing. But pure H2O has no ions of its own, and so it does not conduct electricity. However, sodium chloride solution, okay, remember aqueous means that we are dissolved in water, all right? A water solution of sodium chloride will conduct electricity because I have sodium plus, I have ions in my solution. All right, so let's say I have a light bulb, and I subjected you all to my beautiful artwork this morning in our lecture video, or our class time. We've got a filament, lovely artwork, and I've got my two wires, and they're in a solution of sodium chloride. Right, this is a liquid solution. My light bulb will shine, right? Because sodium chloride solution, sodium chloride in water, will conduct electricity. But in contrast, if I have my wires and they are in a solution, a liquid solution of sugar, we stay dark. Right? Because sugar does not make ions. Right? So I mentioned a little bit ago that acids and bases can also work as electrolytes, because if I have something like hydrochloric acid in water, I get H plus aqueous and Cl minus aqueous. If I have sodium hydroxide in water, I'll get some sodium plus and some OH minus. Right? If I can make ions in water or ions in solution, that means that it's an electrolyte. Okay, now we have some electrolytes are strong electrolytes and some are weak electrolytes. And the difference between those is that strong electrolytes they come apart completely. Okay, something like sodium chloride is a strong electrolyte because all it does is come apart into sodium plus and Cl minus. Right? Weak electrolytes don't come apart completely. Or we say we don't completely dissociate. Okay, so something like sodium acetate. Right, this is our acetate ion. So what we get is actually, we get a double-headed arrow. Right, so some of this is proceeding this direction, and some of it is coming back the other way. So to see what that sort of looks like in solution, if I have a beaker of sodium acetate, I'll have some sodium and some acetate, but mostly I will have the whole molecule together. Okay, so some of it stays together, some of it comes apart. So if any of it stays together, then that means that we categorize it as a weak electrolyte. Okay, and you'll be able, and we'll get into how to tell the difference here in a little bit. All right, so let's talk about how to calculate how many ions we have in a solution. Okay, so potassium bromide is soluble in water. That means that it comes apart. Okay, so it breaks up in water. So if I have some potassium bromide solid, KBr, solid, and I put it in some H2O, I get some potassium plus aqueous and some bromine minus aqueous. Right? So that means that I have 2 ions per molecule. I can also say 2 moles of ions per mole of molecules. Okay, so let's do a little practice. So let's ask the question, how many ions are in a solution containing 1.5 moles of magnesium fluoride? All right, remember I threatened that I would start using just words in our problems, right? So the nomenclature needs to be at the top of your brain, right? So the formula for magnesium fluoride is MgF2. So if I take some magnesium fluoride and I put it in water, I get 1 magnesium ion and 2 fluorine ions, which gives me 3 ions per molecule. Okay, or 3 moles of ions per mole of molecules. So this becomes a conversion factor. All right, I'm going to keep using this strategy of doing conversion factors, using ratios to help us solve these problems. That way you have one method for solving all of these questions. So if I have 1.5 moles of MgF2, for every 1 mole of magnesium fluoride, I have 3 moles of ions. Right? So that my moles of magnesium fluoride go away, leaving me with 4.5 moles of ions. Right? So what if I ask the question, how many moles of just fluoride ions? Right, so we take a look back up here, and I've got 2 fluorines per molecule. 2 fluoride ions per molecule, so I just apply that ratio. So I have 2 moles of F minus for every 1 mole of magnesium fluoride. So just fluoride ions, I've got 3.0 moles. Okay, so using ratios as conversion factors is the most direct and simplest way to tackle these problems. Okay, and I encourage you to write these things out, to use labels, actually write the word mole F minus and mole MgF2. Because it will help you track down if you make any mistakes. It'll help you to make sure that you've got your ratio in the right orientation, all that good stuff. So I'm going to go ahead and stop this video right here, and we'll pick up the next video. We'll finally get into talking about concentrations and molarities.